Welcome to Improper Integrals, Part 2. In the last lesson in Section 8.8, we talked about improper integrals as we were looking at integrating from a number to infinity or from negative infinity to a particular value, or for that matter, from negative infinity to positive infinity. But in this lesson, we're going to look at approaching a particular value, where a or b in those x values end up being a vertical asymptote in most instances. So let's take a look at that right now. So I took this directly from your textbook, and this is just the general outline for what we do when we are in fact integrating when a or b has a value of infinite discontinuity. So if b is the value for infinite discontinuity, again, think of me having a vertical asymptote on the right-hand side of the function. So I would be able to integrate up from a until b, where b is that vertical asymptote. And in order to get around that, I would simply change that b to the variable c and say the limit as c approaches b from the left-hand side. Again, if you think of that asymptote being, again, like we have a graph, and maybe it looks a little bit like this, and we're starting here at a, but we're integrating here to b, but b is that asymptote that we have going on. What we simply say is we say, okay, let's go towards b, but from the left-hand side of that. So we rewrite it using that. This is exactly what we were doing as we were going towards positive infinity or negative infinity. So it's not really any different here. We just have to be very careful about approaching it from either the left side or, as you see in number 2, when we approach it from the right side. And again, that looks a little bit like this graph right here. As I'm going again, I'm starting here at A and going to B. And A is where that vertical asymptote is. And again, number 3, we're just going to break it up. So what do I have if both, in fact, A and B are points of infinite discontinuity? So what does that kind of look like? That may look, say, like the graph of cosecant, which has a vertical asymptote at 0 and another one at pi, and maybe we're simply looking for the area underneath between 0 and pi of again, like I said, this would be the cosecant graph. Just an idea. I don't actually know if we can do that or not, but I wanted to give you an idea of something that could, in fact, be an integral that we could evaluate. Let's look at a couple examples next. So in this first example, we're looking at the integral from 0 to e squared of the natural log of x to the third power. I have that graph here for us, and I also have shaded in the area that we're actually talking about. I think the important thing for you to understand in this problem is that this value right here at x equals 0, that actually ends up being, for me, a vertical asymptote in this particular problem. E squared is here, and e squared is where I've stopped the function. That's a direct ending point. But like I said, x equals 0 ends up being a vertical asymptote. So let's set up that integral now. So let's hear. So the integral from 0 to e squared of, well, I'm going to go ahead and convert this. That's easier, much easier to write it as 3 times the natural log of x dx. That would be so much easier because then 3 becomes my constant. Okay, let's rewrite this using a limit. So remember, what I'm going to do is I'm going to take that a, and I'm going to say, okay, I want to approach 0 from the right-hand side of the expression. And then when I rewrite my integral, I'll go from a to e squared of 3 natural log x dx. Okay, so again, I'm going from the left-hand side. And we'll go ahead and we'll work through the rest of this problem now using the limit. And again, you're going to notice it's not going to be anything different than what we had done in the last lesson. We'll keep that limit there. We'll go ahead. I'm going to use integration by parts here. Not the so I'll let u equals the natural log of x. du is 1 over x dx. dv equals 3. v is equal to, or 3 dx. v is equal to 3x. Then when I redo that, let's see here, the integral of 3 natural log of x dx equals 3x log x minus the integral of, what would that be? Let's hear, 3x over x dx. So So I get 3x log x minus the integral of 3 dx. So 3x natural log x minus 3x. Plus c, of course, which I don't need since this is a definite integral. So I'll go back over here. So I'll take this and I'll plug it back over here in my problem. And let's see here, that'll give me 3x natural log x minus 3x. And again, I'm evaluating that from a to e squared. All right, split it up. Limit as a approaches 0 from the right of 3e squared natural log e squared minus 3e squared. Put that in parentheses. Ooh, minus 3a natural log a minus 3a. What do I end up with? Let's see here. So equals. So what? That's 6e squared minus 3e squared minus, move my limit in, as a approaches 0 from the right-hand side, of 3a natural log a minus 3a. Okay, so let's see here. The first two terms just give me 3e squared, so that's nice. Minus, let me now evaluate the limit. So the limit as a approaches 0 of 3a is, of course, 3 times 0. And then the natural log of a. So the natural log of the natural log is the natural log of a is a approaches 0 from the right-hand side. Let me think about the graph of the natural log. The graph of natural log looks like this. So as I go towards 0 from the right-hand side on my natural log function, natural log of a, that goes towards negative infinity. And then I'd have minus 3 times 0. Oh, no. That's a problem. Oh, no. So what in the world am I going to end up doing there? Let's see here. Well, let's just look at this. So let's just look at the limit as a approaches 0 from the right-hand side of just this 3a natural log a. Because right now, that equals 0 times negative infinity. And that's a problem for me. That's an indeterminate form, which means that in order to evaluate just that particular part of my limit, I need to rewrite it. So let's just do some creative rearranging. We'll write it as 3 natural log of a as a to the negative first power. And then when I evaluate this, and I'm going to skip the work here, if you trust me, what's going to happen is I'm going to end up using L'Hopital's rule now, because what does this become? This becomes, this is a indeterminate form of negative infinity over infinity. So what I'll do is I'll apply L'Hopital's rule, and I'll end up with the limit as a approaches 0 from the right-hand side. Let's see, that's 3 times 1 over a over negative 1 over a squared. When I do that, if I simplify that down, I'll end up with the limit as a approaches 0 from the right-hand side. Let's see here. Well, it's 3 over a squared, so that would be 3 over a times negative a squared. And I'll let some a's cancel out. So end up with a limit as a approaches 0 from the right of 3a, negative 3a, which is in fact equal to 0. So that whole thing up there, now, if I just kind of like think this as a side note for myself, and I go back over here, that's now, we'll write it down over here. That's 3e squared minus, I just evaluated that, 0 minus 0. So I get my final answer of 3e squared as being the area for that problem. Oh boy, that was a long problem. Let's try another one. The integral from 0 to 2 of dx over x squared. I promise, this one is a lot shorter than the last one. Again, what do I have going on? I showed you the graph here. So I have the graph of 1 over x squared from 0 to 2. So 0 to 2. And we, of course, know that here at 0, x equals 0, I have a vertical asymptote. So, again, what does this look like? When I'm evaluating, I'll change and I'll say I'm approaching a from the right-hand side. Sorry, a is approaching 0 from the right-hand side of the integral from a to 2 of x to the negative second power dx. That'll be so much easier to integrate, because when I do the integral, it just becomes so much easier to do. So I'll get negative x to the negative first power, and again, I'm evaluating that from a to 2. So let's keep going. The limit as a approaches 0 from the right, when I plug that in, let's see here, that will give me what? I get negative 1/2 plus 1 over a. Cool. Now when I evaluate my limit, I'll have this negative 1/2, and I'll look at the limit. Well, if I think of the graph of 1 over a, right, the graph of 1 over a, that looks like this, right? That's 1 over a, and I'm approaching 0 from the right-hand side. That's this way. So that right there goes towards positive infinity. And negative 1/2 plus positive infinity is in fact infinity. Wow! So what does this mean? That means that area is unbounded, and this is divergent. So I can't actually, I can't talk and write at the same time either, evidently. This graph is in fact divergent, so I cannot find a value there. It's not a finite number. It is in fact an infinite area in this particular problem. Time for the last problem. Let's check it out. So the integral from 2 to 4 of 1 over the square root of x squared minus 4. So let's look at that. The graph I have shown here for you. So you'll see that, in fact, 4 is where that ending point is, but you'll see at 2, it appears that I have a vertical asymptote. And in fact, I do in this particular problem. I'm going to do this one slightly different. Evaluating the integral in this particular problem ends up being a little bit of a challenge. If you're looking this, x squared minus 4, it kind of looks like arc sine, but it's not arc sine because that would be 4 minus x squared. So in this particular problem, it's not as easy as it may appear at face value. However, you should recognize this as in fact a trig substitution problem. So let's ignore the limits of integration for now, and let's just focus on the integral of 1 over the square root of x squared minus 4 dx. Let's ignore everything else. Let's in fact focus on that. And let us draw this right triangle that's going to help us to solve this. I have my theta value here, knowing that this would have to be x squared minus 4, right? Because we have the hypotenuse, which I know has to be x, and then the denominator, or the other value for the other leg of the hypotenuse is going to have to be 2 in order to make this triangle work out. And again, remember, I want to try to stick to sines and cosines or secants and tangents. And in this particular case, because of the format and the setup, I know I'm going to end up using the secant. And secant is equal to, of course, the hypotenuse over the adjacent side, so x over 2, which means x is equal to the 2 secant of theta, which means dx is equal to 2 secant theta tangent theta d theta. And then tangent of theta, we know tangent is equal to opposite over hypotenuse, so that's the square root of x squared minus 4 over 2. I'm sorry, opposite over adjacent. I think I said opposite over hypotenuse. I know that's not right. Tangent is opposite over adjacent. So square root of x squared minus 4 over 2, which means that 2 tangent of theta is equal to that x squared minus 4 when I need that to substitute that in. So using that information, I will now rewrite my integral using my trig properties. And let's see here. So I'll have the dx, and we know that dx is 2 secant theta tangent theta d theta over, and I know the square root of x squared minus 4 is 2 tangent theta. And if this, oh wow, this works out really nicely, doesn't it? Because look here, tangents cancel, 2's cancel. So my integral, after I cancel those things out, is simply the integral of the secant theta d theta, which I know. That's the natural log of the absolute value of secant theta plus tangent theta, plus c, of course, in this particular case. And then when I substitute back in for secant and tangent, the way it was in the original problem, and if you allow me to skip a couple steps here for you, I'll end up with the natural log, oops, hold on, let's make the magic happen. Magic happens there. We end up with the natural log of the absolute value of x plus the square root of x squared minus 4. Plus c, of course, which we won't eventually need, but it's nice that we have this shortcut for this integral. Okay, let's keep going with this problem now. So now, let's put in the limits of integration, or let's use from the 2 to the 4. Remember that I'm going to have to use a limit to represent that 2, because it can't actually get to the 2, but I want to approach it from the right-hand side of that graph. So I'll integrate from a to 4. And again, this is 1 over the square root of x squared minus 4 dx. Now, lucky for me, I already did the math, and I know that that limit is equal to, as a approaches 2 from the right-hand side, and the integral, which I already have, is the natural log of x, the absolute value, of x plus x squared minus 4, from, again, a to 4 in this particular problem. So by doing that integral ahead of time, I saved myself some work as I did the problem. And now I just got to plug my values in. So let's see here. I get that this is equal to, well, I plug in the 4, I don't need the limit, so it would be the natural log of the absolute value of 4 plus the square root of 4 squared minus 4. That's the first thing. Minus the limit as a approaches 2 from the right-hand side of the natural log of the absolute value of a plus the square root of a squared minus 4. In the absolute value, close the bracket. Let me just clean that up a bit right there. Okay, good. All right, so now what? Let's see here. When I did the math over here, 4 squared minus 4, this is the natural log of the absolute value of 4 plus the square root of 12. Okay, minus, let's see here. What happens when I plug 2 into this problem? Let's see here. Well, okay, so it's the natural log of the absolute value of, well, as a approaches 2, that's just 2. And what happens as a approaches, well, okay, so that gives me 2 squared minus 4. 2 squared is 4, 4 minus 4, so I get plus the square root of 0? Well, that kind of worked out really nice there for it, didn't we? So let's see here. I get the natural log of the absolute value of 4 plus, well, 2 square roots of 3, if I simplify down that radical, minus the natural log of 2. Folks, that's the answer. That's got nothing but numerical values. That would be acceptable, but I think we can do better. So let's condense this a little bit. So the absolute value about the 4 and the plus 2 square roots of 3, not necessary, right? 4 plus 2 square roots of 3, that's a number, a positive number. So I can just forget about those. 4 plus 2 square roots of 3, parenthesis, minus the natural log of 2. Subtraction with logarithms turns into a division when I consolidate that. So 4 plus 2 square roots of 3 divided by 2. Oh, and look there, everything's divisible by 2. So I get the natural log of 2 plus the square root of 3. That is the final answer for this area up here in green. All right, guys, thanks for sticking with me through this lesson. Problems were not that, I just wanted to show you a variety of different problem types that you could possibly see. Sorry that all of them seem to be approaching from the right-hand side. That doesn't have to happen. I just happened to pick 3 example problems where they were all approaching from the right-hand side. So just be on the lookout for that as you do some of your homework problems. Speaking of homework, here's your homework assignment. Take a look at that. If you have any questions, we'll, of course, go over this next class. See you then.